All right, everyone, welcome back to the final video, I think, of the midterm review. In this one, we're going to be talking about energy bands, and we're going to do a couple of examples uh, on energy band type questions. So without any further ado, we're just going to jump right into it. So actually, before we do, with a little bit of further ado, you need to be able to figure out if something is an N type or P type semiconductor or material based off of its energy band diagram. So again, I'm not doing too much theory about what is an energy band diagram or how we come up with them, etc., etc. That's up to you to figure out. I'm just going to tell you some testable stuff and some stuff that I think quick intuitive things we can pick up on. So if we have here E2 and E1, and I draw a picture and I tell you the Fermi energy level, EF is there, and the halfway point is there, you should be able to tell me whether or not this is N type or P type just from looking at this, okay? So if you can figure it out, great. If not, this one is a P type. Okay. Because the Fermi energy here is closer to the E2 or EV than it is to the C conduction band. Okay, so you should also be comfortable if they ask you if a question here says of these two energy bands, which one is the conduction and which one is the valence energy band, you should be able to say that this is EC and this is EV or valence. And if they ask you which direction does energy increase in, does it increase going down or going up? The energy increases going towards the conduction band, because if you have a nucleus, right, if let's say that's the nucleus, that's E1. Sorry about that. Let's say we have here E1 and E2. This is the valence band, right? So the energy of electrons held at the valence band is lower than the energy of the electrons held at E1. Okay, so this is EV and EC. Okay, so let's go ahead and do an example. So consider the energy levels shown in this figure. The probability that an energy state at E equals 1 is occupied. So there's a couple things here. First of all, is occupied is a huge one. Okay. That is occupied by an electron is 2.3, and it's occupied by an electron. So these are two different things that are both important. And we need to find EF minus E2. Okay. So what they're telling us is that they're saying when E is equal to E1. Now this I noticed a lot of my students got confused with. All it's saying, okay, all it's saying is when we have these equations, for example, the probability of finding an electron is 1 plus E minus EF over KBT. When they're saying when E equals E1, all they're saying is that here we're going to put E1, and that now that one there becomes E1 as well. So they're saying the probability, so this is 2.34. Okay, let's go ahead and start. Is 2.34 times 10 to the negative 4 is equal to 1 plus E. This should be E1 now, right? E1 minus EF over KBT. Now, what we need to solve for first is E1 minus EF. So if we solve E1 minus EF, then from there we can find EF minus E2, which is the thing that we actually have to find. Okay? And a lot of times, students will make the mistake where they're going to give you the probability as related to one of the energy states, but ask you a question about the other energy state. So be careful for that, okay? Oftentimes, I had a lot of students who found this difference, which is what we're about to do, but then they forgot to take the next step, okay? So from here, we're going to take this here and put it under the denominator and put this entire thing and bring it to up there. So it becomes 1 plus E E1 minus EF divided by KBT is equal to 1 divided by 2.34 times 10 to the negative 4. So this one I'm going to change it right away to, actually I didn't write it down. So maybe I can get my calculator. So 1 divided by 2.34 times 10 to the negative 4, we get 4,273.504. So the next step here in simplifying this would be to bring the 1 over. So we get E1 minus EF divided by KBT is equal to 4272.504. Now we take the ln of both sides. So on the left side, we're just going to be E1 minus EF over KBT is equal to ln of 4272.504. And ln is, ln of 4272.504. And then we multiply by KBT. So E1 minus EF. KBT is, KB is the, I think, Boltzmann constant, if I'm not mistaken. But KBT in your formula sheet at 300 degrees is given as a constant, right? So at 300 degrees, which is a commonly used temperature, it's 0.026 EV times, and the ln of that number was 8.3599. So E1 minus EF equals 0.21. 0.217. Okay, so a lot of students, and if I was to write this question out, I would give this as an answer choice because I know a lot of students would pick it. Okay, and a lot of times students want the final answer, so they just will be like, okay, like this is EF minus E2, like, okay, I'm just gonna say this is EF minus E2 as well, even though it's not. Okay, so now the next step is to say EF minus E2. Now we have the full band gap, which is 1.12 EV minus 0.217 EV, or 0.904 EV. So you could also have a situation where they don't tell you the band gap difference. They don't give you this 1.12, and they tell you just the material. So if they do that in the formula sheet, again in the back, I'm looking at it right now, they have the band gap energy. And so for this one, it's 1.12. So from according to the formula sheet, this is silicon. Okay. So that's a good example here of things you can find. And recall that this is the probability that it's occupied by an electron. Okay. They could have asked us, what is the probability, if they could have said the probability that it's occupied by a hole is 2.34, or that the probability that E2 is not occupied by a hole is 2.34, whatever. So be careful, okay? So it can be probability that it is occupied, it isn't occupied, and that it's occupied by an electron or a hole. Okay? So that's the first example. And we're going to do another one here. So a germanium crystal at T equals 300 K is doped with 3 times 10 to the 7 acceptor atoms per centimeter cubed. The Fermi energy is blank with respect to the middle of the gap. And then they give us some choices here. So first, recall that we have Ni squared is equal to NOPO. In this case, Ni, in this case, we have intrinsic concentration according to the formula sheet for germanium is 2.4 times 10 to the 13. Okay. And then we have this, we need to figure out what is it with relation to the middle of the gap. So first of all, we should recognize that when something is doped with acceptor atoms in particular, acceptor atoms means that this is going to be p-type or n-type. Should be p-type, right? Because they're acceptor atoms. And we also have this relationship that says the concentration of of donor atoms minus the concentration of acceptor atoms is going to be the same as the difference between the concentration of electrons and the concentration of holes, PO. So in this case, look at the difference. We're doping it with 3 times 10 to the 17 acceptor atoms when the intrinsic concentration is times 10 to the 13. So we can essentially say that the number of acceptor atoms are so large that our intrinsic number of concentration of holes and concentration of electrons don't even matter anymore. And what we can say here is that we have Na is equal to, or roughly equal to, I guess we can say, PO. And then from the formula sheet, we also have EF minus EV is equal to KBT ln NV over PO. NV here is it's again from the formula sheet. It's called the effective density of states in the valence band. So the number of the number of states that are within the valence band. Okay, so within a given volume, unit volume. So here, NV, looking up from the formula sheet, is for germanium. Let's take a look. Effective densities. NV 6.0 times 10 to the 18. And then because we said that Na is roughly the same as PO, and we have PO down there, we can replace it, and we can say EF minus EV is equal to 0.026 EV ln, and then 6 times 10 to the 18 divided by 3 times 10 to the 17. And that's 0.77 EV. But again, don't fall for just the very first thing that you get an answer for. We need to know what it is with respect to the middle of the gap. What we just found is, let's say this is EC and EV. We just found the Fermi energy level minus EV. But what we want to do is figure out with respect to the middle of the gap. So what we need to do is go to the formula sheet, look up the band gap energy, which is 0.66, divide that by 2. Okay, divide that by 2, which will tell us where our halfway is, and then figure out what the difference there is. So we should have here, so let's just see, 0.33, right? It's going to be 0. So band gap energy for germanium is equals 0.66 EV. So the halfway point, this is 0.6, yeah, the halfway point is 0.33. So it's going to be 0.33 minus, right, minus 0. Sorry, this should have been 0.07. 0.077 EV. Did I do something wrong here, actually? This should be, no, I think it should just be 0.66 minus 0.077, no? Let me see. Did I make a mistake here? Because we have EF minus EV. No, I think that's correct, yeah. So the answer should be 0.25 EV below. Okay. So here, the answer was C. Let me see. I think, yeah, that's pretty much all the questions that I wanted to go through. And then the last thing I wanted to go through is you should be able to, as I mentioned, you should be able to figure out PN junction band diagram. So PN junction band diagram. So we didn't really talk much about PN junctions, but the semiconductor, two semiconductors, one P type, one N type, and these together called a diode. Okay, so I think for your midterm, you should be able to draw the diagrams or recognize from the diagrams. So if this is a P type, should be E, C, E, V. The halfway point is E, F, I. And then we'll call this one EF. So the Fermi energy is there. And then for the N type, so the thing you need to keep the thing you need to keep in mind, the default is that a p-n junction, the Fermi energy stays the same. However, for n types, the distance between EF and EC is smaller. Is smaller than the distance between EF and EV. So EC, EV. And so what happens here is that you get a drop like that, and then this would be for the middle of this one here. Okay, so this is a p-n junction energy band diagram, and you should be able to recognize when it's p-n, np, and then so this is called a zero biased. And essentially what it means is this is what happens when there's no current going through the junction. But again, you should be able to recognize when is it zero biased. Is it zero biased? Is it NP or PN? So if you're seeing a drop like this, right, that'll tell you it's P and then N. Think of this as you have a ball and you need to roll up this electron up the hill, okay? And I'll show you why that's a good way to think about it in the next slide. So the next configuration is forward biased. So how diodes work is that they allow current in one direction but not in the other direction. So this forward bias is when the positive terminal connected to the p-type. And when you're looking at a circuit diagram, if this is positive and minus, this is what diodes look like in circuit diagrams. So you have a triangle and a little line like that. And then this would be a p-n junction. So this, in this current setup, current flowing in that direction, that is a-okay. This is called a forward bias. So let's draw the diagram and figure out what's going to happen. So we have, I'm just going to bring the p. Okay, let's bring, let's bring all of these with us. Oh, what's happening? Oh. Copy. So paste. Okay, so in this situation, we have our P side like that. However, what diodes do, they make it easier for the current to go through, and they do that by raising the Fermi level by some amount. So no longer is it constant. Okay, so this is EF. Again, the conduction band on the n-type, so this is n-type side. Remember that the conduction band, conduction band on the n-type side is going to be closer to the Fermi than the valence. So EC, EV. Now it's going to look something like that. So imagine, remember I told you can think of this as you have to take this electron and push it up this hill. This hill is much smaller slope than it previously had. Okay, so by moving the shifts up, so forward bias shifts up EF, and so everything else also shifts up a little bit as well. So again, what the theory behind this I'm not covering in this video. You have to go figure that out on your own. Okay, so it's just a quick midterm review. So, and then finally we have backward bias or reverse. Backward bias or reverse. And in this case, the current is hooked up the other way. So positive terminal to N-type. And now let's take a look. Actually, let me just, can I paste? Paste. Awesome. So there's our P-type. Now, though, the Fermi energy level is going to drop. So it's going to look like that. And everything else drops with respect to it as well. So EC, and EF. Or sorry, EV there. And now it's got a huge slope, the hill. Okay. So now to push this electron up this hill, very hard. So you don't get the current going through. So you need to be able to figure out, just from looking at a band diagram, is it forward biased or reverse biased by looking at the EF? Is it constant? Is it going up? Or is it dropping? And you need to also be able to figure out, is it, where are ECs, EVs going to be labeled? And also, is it P-type to N-type or N-type to P-type? Okay. So, or which side of it is N-type, P-type? So keep in mind that if this was N and then P, then it would be it would look different, right? So keep that in mind as well. So I think that's everything that I have for the midterm review. I had some other example questions, but I think that's enough for me to leave you with today. I wish you the best of luck on your midterm, and don't forget to do your best. Good luck. And if you want to subscribe to the channel, you can. I don't know what kind of content I'll be putting up or how often, but I do want to kind of start a, tutorial style or educational style channel here where I talk about interesting concepts related to physics, as well as my own research and my own field of medical physics as well. But anyways, good luck on your midterm, and take care. Brush your hair.